Okay, I think for the today's session, we still will discuss about how can we supply water as part of the utility system. Previously, we have discussed about in brief about the water cycle, and then what kind of characteristic, the general characteristic of water from different sources. We also have discussed brief about what is the purpose of water usage in industry. So basically, it can be as a raw materials for such as in the beverage industry, or you can use it as the utility system. Utility is basically classified for the direct activities. It means water is directly involved in the process as the process water, or in the steam in the boiler, in the cooling system, or any process that related to the production. But water can also be used for the indirect activities, such as for cleaning, for the drinking water system, and also for fire extinguishing. And depend on the source of the water, I think, depend on the source of the water, the characteristic of the water is different. And we have also learned about the specific features of water that basically with water is the universal solvent because it has polar characteristic, and then it has positive ions and then negative ions, and also hydrogen bond between the molecules. The polar characteristic of water shows that water can dissolve almost all compounds. Remember again that during the hydrologic cycle, water will go through plants, rocks, sands, and etc. And also it can mix with the gas at the deep water, at deep well, also with oil. And so the compounds that contain in the rock bed or in the sands can dissolve in the water. And this is the main water impurities. It can be non-ionic or in suspension substance. It can be in gas and in ionic, and we call it dissolved substance. Basically, dissolved substance or the ionic substance is the main problem with water if we want to use as utilities or as process water. This is the ionic impurities. It can be positive. Ion means you can have it in positive and negative ions, and some ions have certain characteristic that later will influence the process if the ions is not removed or is not reduced. Okay, for example, is silica. We have I have mentioned about this one. So basically, silica have different types in the water. It can be in suspended, but in suspended, it's relatively easier to be removed. But if it's in dissolved state, generally it will be in the acidic form. Yeah, in the acidic form, but it is low acid, weak acid. Sorry, yeah, it become asam lemah, weak acid. It means for the removal, it's also difficult. If you have a concentration of silica in water, then during the process, silica can create scale, and the scale is very, very sticky. It's very hard, and it can damage the boiler, for example. Okay, so as a universal solvent, this is types of common dissolved solid that you normally found in the water. It can be in the calcium base, magnesium base, silica base, sodium base, or iron base. Actually, there are more compounds that dissolve in the water, but these 5 compounds, these 5 major category is normally quite significant, have quite significant effect when the water is being used in the industry. Okay, now we go to the hardness. Yeah, due to the mineral content, some of the dissolved solid content in the water will possess properties that called hardness. Maybe before we go through this hardness in general, maybe I will ask, what do you know about hardness? Gamma?
Yes, sir.
Yeah, have you heard the term hardness or hard water?
Yes, sir. It's the amount of mineral content in water, right? So like hard water, for example, would leave scales and things and like your things at home, for example.
Okay, yeah, that's correct. But normally when you deal with hard water in daily life, what will be the effect of hard water before it creates scales in the operation or in the scale is the main problem caused by water hardness. But beside for the industry in daily life, or why this is called hard water? If the mineral content from calcium and magnesium, right? If the content is quite high, it's called hard water. Why it's called hard water? Anyone knows? Atau bukan secara industri lah, kalau secara kehidupan sehari-hari ya, daily lives, what will be the effect of hard water? Air sadah kalau in Indonesian.
Yep. Are one of them such as like stain yang menyebabkan kerak seperti itu?
Not stain. Stain is basically from other component, normally manganese or iron, but this one comes from calcium and magnesium. Scale is the problem, but before scaling, using hard water, there will be like a certain effect. I don't know whether now you know or not, but I think Pak Hendra will know. Ada yang tahu? Kalau Anda menggunakan air sadah, biasanya efeknya apa? Sebelum ke industri.
Is it something to do with your kidneys, sir? Maybe? I don't know.
Oh, if you drink it?
Yeah.
Maybe. Okay. Probably, yeah. It will scale your kidney, probably, yeah. But before that. Have you go to the, I don't know, coastal area near ocean, and then, but that's not because of the salt, not because of the sodium or chloride. This is because of the calcium and magnesium. When you go to the, well, if you go to the nice hotel or nice resort, I don't think you will have the experience. But if you take like well water from the well, it's not seawater, not brine water, but you take the water from the well, but the location might be near the ocean. Have you experienced when you take a bath or you do the laundry?
Does the water taste bad, sir?
Not about the taste, but when you mix the water with soap, for example, if you want to use it for taking a bath or you want to do the laundry, if you use hard water, what will be the effect? Pernah nggak mengalami? Ini jangan-jangan anak zaman sekarang nggak pernah, Pak Hendra.
Kayaknya udah bukan ini, Pak. Bukan zaman.
Traveling.
Ya. Mencuci atau mandi yang dekat pantai nggak pernah merhatiin sebegitunya sih. But, jadi nggak yakin juga.
Or if you go to, have you go to Pangandaran? when you go to Pangandaran, you know Pangandaran, right? Then you go to the not the high quality hotel, but you go to the motel or the cottage like that. Have you encountered that it's difficult to foam a ladder from the soap with the water from the hotel? Ada yang pernah? Nggak pernah juga.
But is it the smell that you're talking about, sir?
Not the smell, but
Leather.
if you
The intake, sir?
sorry,
The intake of the soap. We use more soap.
yeah, you need more soap to create
make
bubbles, to
yeah.
create foam.
busa.
Busa. Jadi kalau buat mandi butuh banyak sabun gitu sampai benar-benar berbusa. Pernah nggak kalau pergi ke Pangandaran dulu sih? Rasanya salah satunya Pangandaran. Pernah?
Kalau di hotel sih biasanya ya. Di hotel kan suka.
Iya.
Ya,
or
motel.
hotel near the pantai, near the ocean. Normally the water is quite hard. It's because of the calcium and magnesium. It will create scaling, of course, but you can test by yourself the hardness of the water by putting soap. If it's not, but use your detergent or easily lathered soap. Don't use special soap, of course. So if you use soap, normally it will lather up quite easily, right? But sometimes the foam is difficult to produce. It means the water contain quite concentration of calcium and magnesium. That's what we call hard water. In contrast, soft water have low mineral content in terms of calcium and magnesium. Ya, air sadah, bukan air keras ya. Hard water is translated as air sadah. Kalau air keras beda lagi, itu campuran. It's the mixture of, what is it, Pak Hendra? Is it chloride acid and something? Do you know, Pak Hendra, air keras?
Oh, the air keras ya Pak ya?
I
think is the hydrochloric acid if I'm not mistaken, Pak.
Yeah, hydrochloric acid combined with another acid if I'm not mistaken.
And also with the high content of the minerals as well.
Yeah. That's different. That's you used to membekukan atau mengkakukan organic matter. This one is air sadah in Indonesia. So the main feature or untuk mengetahuinya secara gampang, you can just put soap. If it's not lather up easily, then it's hard water. So hardness is calculated by ppm or milligram per liter calcium carbonate. Normally, the unit will be ppm calcium carbonate. The higher the concentration, it means the water is very hard. Okay, actually this slide I just add, but you can find this slide also in the second slide about cooling water. But it has a quite detailed explanation about hardness. So basically, we can classify hardness in two types. First is temporary hardness, or we call it kesadahan sementara. Temporary hardness is from calcium and magnesium, but with bicarbonate. Ya, jadi anionnya ya, jadi kationnya itu, the cation will be calcium and magnesium, and the anion will be bicarbonate. Why we call it temporary? Because we can reduce this hardness. I mean, you can treat normally, previously it's by using heating. Yeah, you can reduce the presence of the metal cations, makes the water hard. But this hardness can be reduced by either boiling the water or addition of calcium hydroxide, lime. We call it lime softening. The boiling of the water will induce the formation of carbonates. Bicarbonates is dissolved and the carbonate is not dissolved. Yeah, so it will be precipitated. It becomes calcium carbonate will be precipitated, mean the appearance will be from dissolved into solid. So it will be precipitated, and then you can separate the solid. Okay. Vice versa, permanent hardness atau kesadahan tetap. This permanent hardness is generally difficult to remove by boiling. So this type of hardness is caused same calcium and magnesium, but the anion will be sulfate chloride. Yeah, so it can be in the form of calcium sulfate, calcium chloride, or magnesium sulfate or magnesium chloride. It will not precipitate if you boil the water. That's why we call it permanent hardness. How to treat the permanent hardness? Normally, it's using other chemicals. We call it water softener. We will discuss it when later we discuss internal treatment, water softening, or using the ion exchange. Okay, this is the type of hardness. So the calculation of hardness is done by using or by calculating the total hardness. So total hardness can be calculated from cation side or from anion side. So total hardness in cation form is the total between calcium and magnesium. So it quantify both cations, calcium and magnesium. However, later we will see that you cannot directly sum up the concentration of calcium and magnesium because each have a different weight number, right? It has different height number, and also the valencies will contribute to the hardness. So the calculation will be in equivalent. Later we will discuss. And in anion side, the total hardness in anion form could be calculated by two methods. First is the carbonate hardness that we call the temporary hardness, and the other one is non-carbonate or the permanent hardness. So basically you sum up the total hardness from the bicarbonate content, yeah, of the compound containing the carbonate and bicarbonate content with the non-carbonate. Again, the calculation is also in equivalent because we cannot directly sum the concentration. Okay, related to the hardness, the water also have what we call alkalinity. So alkalinity, water alkalinity occurred because there are some alkaline substance. You know alkaline, right? Basa, the opposite of acid, the alkaline substance in the water. It can be from the hydroxide compound, or carbonate compound, or bicarbonate compound. Yeah, so it's from the anion side, whether it's in hydroxide, in carbonate, or in bicarbonate. And please remember again how to determine the concentration of alkali. Then you have to use acid solution. So normally to calculate the alkalinity level of the water, we are using the simple titration method. Yeah, using chloric acid solution, and to calculate the number of the alkalinity, we can follow up the titration with the neutralization using two types of indicator. First is phenolphthalein. What is the color of the phenolphthalein? Anyone still remember?
Pink, sir.
Pink. Okay. Is it correct, Pak Hendra?
Yes.
Actually, I forgot.
Pink, Pak, yes.
Okay. So two different indicator with different color. First is phenolphthalein. We call it P alkalinity, and the other one is using methyl orange or methyl jingga kalau dalam bahasa Indonesia. We term it M alkalinity. What is the relation between hardness and alkalinity? So basically, we have discussed, right? The hard water comes from the high mineral content from when water percolates to the deposit of can be a limestone, chalk of bitumen, and these minerals are largely made up of calcium and magnesium carbonates, bicarbonate, and sulfates. If we use hard water in industry, some problems may occur, right? Like falling and then scaling. This scaling and falling can damage the internal equipment of the boiler, such as the tube. And in domestic setting, hard water is, I think we have, I have told you, in domestic setting, hard water is often indicated by lack of foam formation. When you mix the soap with water, and by the formation of lime scale in kettles and water heaters. Ya, jadi kalau masak air pakai air sadah, itu lama-lama di dalam kettle-nya, kettle itu apa sih? Teko ya? Bukan teko ya? Apa sih? Yaitu, the kettles or the water heaters, there will be like scaling. Hard water or the hardness, one of the component of the hardness is from the carbonate, right? And the carbonate itself also have the alkalinity properties. So alkalinity of water is basically measuring the water capacity to neutralize the acid. A water body with high level of alkalinity, will have usually will have high level of calcium carbonate, because carbonate is the main compound that we found in water alkalinity, which can decrease the water acidity. Why we need to decrease the water acidity? What will be the effect if you use water with low pH, in industrial process?
Corrosion, sir?
Yeah, corrosion. That's the main problem. Therefore, the alkalinity measure how much acid that can be added to a water body before not acid, should be base, ya. Jadi alkalinity itu nanti akan menunjukkan Anda tuh perlu menambah basa seberapa banyak agar pH-nya bisa berubah. So basically, the alkalinity will correlate with the corrosion prevention in process industries. Alkalinity and hardness is serupa tapi tidak sama. It's fairly similar. They both from the similar sources in nature. Like when you have limestone and dolomite dissolved in water, half of the molecules will be this one, calcium and magnesium, which quantified as hardness, and the other half will be the carbonate, which quantify the alkalinity. This means the calculation, the level of water hardness and alkalinity usually is a bit similar, but they need different measurement, to measure hardness and to measure alkalinity. The procedure is different, and it will have different importance. Like, in summary, it's like if you have water, you do not want this water to have high hardness, because if you use the water with high hardness, it means the tendency to make scale is high. Right? But this hard water also have carbonate compound, as the temporary hardness. This carbonate compound will contribute to the alkalinity, and this alkalinity actually is important because we want this water to be the pH of this water is safe enough in order to prevent corrosion. Kira-kira begitu ya, kebayang ya. Jadi ketika menurunkan kan pengennya tuh hardness-nya jangan terlalu tinggi gitu. Karena kalau hardness-nya terlalu tinggi, nanti scalingnya gede. Tapi kalau Anda menghilangkan hardness, berarti kan nanti yang hilang termasuk yang karbonat tadi kan. Berarti nanti alkalinity-nya juga bisa turun. Tapi kalau alkalinity-nya turun, nanti pH-nya bisa turun juga gitu. Padahal kalau air itu pH-nya terlalu rendah, bisa menginduce corrosion. Something like that. So both are quantified with different separate method, and have different importance. Okay, I won't explain details in calculation of hardness and alkalinity, but this bar chart correlates hardness and alkalinity both from the cations and from the anions. You can calculate total hardness, you can calculate carbonate hardness and non-carbonate hardness, and you can calculate alkalinity. It should be balanced, not similar, but balanced. So please, I have distribute, I'm sorry, it's still in Indonesian language. I hope it's okay with you. So it's the book from Pak Heri, yeah. I think I already given to Kevin. Have you distributed, Kevin?
Not yet, sir. It's still with me. It's the Dropbox, right, sir?
Yeah, you can download and share to your friend, or you can share the link and because I cannot share it in EduNext, right? It will be against the law. So I share it internally. Just download the ebooks. One is in Indonesian. You go to the example 9.1 and 9.2. Then you will learn how to calculate the alkalinity and hardness and how to correlate these two parameters. Okay, any question so far? Atau Pak Hendra mau menambahkan, silahkan Pak.
So maybe regarding the reactions, yeah. So as mentioned by Pak Wawan regarding the neutralizations reaction, so it consists of 2 steps, yeah. Previously, it's used the phenolphthalein. So the phenolphtaleins will change the color to the pink when it actually mix, yeah, between the acid and the base, yeah. So previously, phenolphthalein is actually colorless, but so colorless, and if it's actually react with the so the reaction between the hydrochloric acid with the alkaline, yeah, whether it's actually hydroxide base, carbonate base, and bicarbonate base, it will actually change the colors from the colorless to pink, yeah, while using the methyl orange in order to get the concentrations, yeah, I think, yeah, concentrations of the alkaline.
Okay. Thank you. Because I already kind of forget how to do the reaction.
Yeah, Pak.
I think they learned in MPA, is it?
Yeah, MPA. So it should be learned in MPA.
Okay, please do not forget the lesson that you get from the MPA.
Hopefully they didn't forget, Pak.
Okay. Any question from the student? Okay, if you have no question, that we will go to the how to not to quantify, like how to quantify, how to mention or how to state the level of impurities in water. What will be the unit that normally used to state the impurities level in the water? So once is that percent of weight. Yeah, this is, I think, the one that you already common with. This is the mass of the impurities divided by the mass of the water. But for the impurities in the water, like the total dissolved solids in the water, we rarely use with percentage, because this percentage is mostly used if you have high concentration of dissolved solid in the water. Yeah. So for that one, we use this ppm unit, part per million. So this is the weight of the dissolved substance per 1 million weight of solution. Jadi 1 per sejuta. Ya, jadi 1 ppm is 1 kilogram of substance per 1 million kilograms of solution. If the density of the solution is 1 kilogram per liter, yeah, if you can assume that the density is the same as water density, then basically ppm is the same as this one, milligram per liter, equals to milligram per kilogram or ppm if the solution is diluted. Ya, ini sama. Miligram per liter dengan ppm itu sama. Kalau densitasnya disamakan dengan densitas air. Ya, ini adalah basis massa, ini adalah basis konsentrasi. Kalau densitasnya sama dengan air, sama. Okay, then from this correlation, how much is 1% of weight? How much ppm? Kalau 1% itu adalah ini ya, 1% berat itu berapa ppm? Come on, quick count.
0.1 sir.
0%? Of course not.
Bentar, million teh berapa nol sih sir?
Million is juta.
Juta ya, so
6.
So 1% will be how much ppm?
10,000, sir?
Yes, 10,000. So you can imagine quickly how much is 1%. So it's around 10,000 ppm, quite big, right? And later you can I think we also I have shown you the table of water requirement for boiler or for cooling water. The order will be just like 10 ppm or maybe 20 ppm or perhaps it's 1 to 5 ppm, something like that. So it's very, very small. That's why we are using ppm unit instead of percent, because 1% is 10,000. It's a lot. Okay, the other unit that previously used is grain per gallon. Yeah, grain per gallon is like a British unit, and this is the conversion. Okay. Okay, how about the calculating the because for the hardness of or the alkalinity, we have calcium and we have magnesium. Calcium and magnesium is two different cations, right? So if you want to take account both cations and sum it and dan dijumlahkan, the calculation of total hardness basically are using equivalent per million. Equivalent per million of the component. EPM is ppm. ppm is definition is this one. So ppm directly correlated with the concentration, right? Because 1 ppm is equals 1 milligram per liter. So EPM is ppm divided by the equivalent weight, berat equivalent, where the equivalent weight is defined as the ion weight or the molecular weight divided by the valencies. Valencies, I think you still remember, right? The ion charge of the compound. So for calcium, the molecular weight will be 40 and the valencies will be 2 and the equivalent weight will be 20. Then the EPM will be depend on the concentration of the calcium. Okay. Okay, this is how you can if you test the water, and then you can get these types of calculation. So for Na, Ca, Mg is the cation side. This is the anion side. You have the ion weight. Hopefully, you can recheck if then the valencies, and then the equivalent weight. This one divided by this one. Okay, you have the data. This is the ppm. This is the ppm. If you sum up the ppm, it will be different, right? But this doesn't have any meaning. If you just sum up the concentration for each ion, it doesn't have any meaning. You need to convert it into the EPM. So from Na, the EPM will be 32. So this one divided by this one divided by this one, you have this one, and then from the anion side, you have this calculation. Okay, from this data, you can check, so the EPM from the cation side should be the same as EPM from the anion side. Paham ya? Jadi perhitungan konsentrasi itu nggak bisa langsung dari ppm, tapi harus sebagai EPM. Bisa dilakukan dari sisi kation, bisa dilakukan dari sisi anion. Okay. The calculation from anion side and the cation side should be the same. Kenapa? Why? Nadifa, are you there?
I'm here.
Yeah, why the calculation of the cation EPM in terms of EPM should be the same as EPM calculation from the anion.
Is it because they form ionic compound?
Yes, so?
And the charge will cancel out each other.
Yeah, okay. Okay, so your answer is not wrong, but basically this is because both are present in the water, right? So all if you do the calculation of concentration, because the raw data will be like this, right? So you test how to get these numbers, by the way. Suppose from the test, you get Na plus, Ca2 plus, Mg2 plus with this concentration, and the anion with this concentration. Basically, this number, sorry, not this one, but the ppm one. The ppm numbers represents the concentration of all the compounds in the solution, right? All the dissolved solid in the solution. Ya kan? Angka-angka ini itu didapatkan dari pengukuran konsentrasi dari senyawa-senyawa so if the calculation already represented all the the dissolved solid in the water, yeah, if you convert it into the EPM, the total should be the same. Ya, jadi kalau pengukuran konsentrasi ini sudah berhasil mengukur semua TDS ya, total dissolved solid di dalam air, maka ketika dikonversi menjadi EPM harus sama dari sisi kation dan anion. So basically the calculation of EPM is to normalize the each concentration of the ions into the similar baseline, ya, kira-kira gitu. Jadi kenapa perlu diekivalenkan, pakai ekivalen, karena itu tuh menghitung konsentrasi, tapi dalam basis yang sama lah, kira-kira begitu. If you do not get the numbers similar, it means that the concentration value here still do not represent every TDS inside that water. Ya, jadi pengukurannya kalau misalnya menghasilkan IPM yang beda, ya, antara kation dengan anion, itu artinya ngukurnya masih belum benar di sini. Datanya kan di sini. Artinya apa? Ada senyawa yang belum terdeteksi. Okay.
I have a question here.
Yes.
Why is it that for the cation and the anion, when we try to make it to the baseline, why do we use the valence electron? Why don't we use something else to base it in?
Sorry, can you say it more clearly, because I think your connection or my connection is quite bad.
Yes, sir. When you put it in the same baseline, why do you use valence electrons?
Why you use what?
Why do we use the valence electrons?
The valence, but the valence, the ion charge.
Yeah, because the valence and the ion weight, we calculate what we call equivalent weight, right? Because each of the ion will have different weight, but with different valence. So like this one, Na and Mg, the molecular weight, the ion weight is similar, right? Like around 23, 24, but the valence is different. That's why the equivalent weight will be different. It's like counting the mass of each electron that they have. Mungkin gitu ya, gampangannya ya. Jadi kayak menghitung berapa berat tiap elektron yang dipunyai dari si senyawa tadi. Jadi walaupun sama-sama 23 atau 24, ini kan cuma punya satu elektron bebas, ini punya 2 elektron bebas. They have 1 free electron, this have 2 free electron. That's why for each free electron, the mass is different. So when you calculate the concentration, because when you have NaCl, it will be dissolved at NaNCl, right? But if you have Mg, no, just a sec. But I hope I answer your question correctly. If you have Cl with Na, it will be NaCl, right? But if you have Mg but Cl, it will be this one, right? So for each Mg, it will have 2 Cl. But for each Na, it will have 1 Cl. That's why you normalize the valencies with the molecular weight.
I think I will add something. But
okay.
Regarding the weight, yeah. So we have to use, I think, the proper terminology. Yeah. For this case, I think it will be better to use relative atomic mass, Pak. So
okay, relative atomic mass is this one, right?
Relative atomic mass is the AR, yeah. We call it AR, Pak. Kalau
this one.
Yeah, AR. But for the if we say that relative molecular mass or molecular weight, it actually represents the MR, yeah, Pak.
Yeah, it's a compound, right?
Yeah, it's a compound. Yeah. So if we have NaCl, so we can say that the molecular weight of the NaCl is 58.5. Yeah. So I think and I think there's actually one mistake in here regarding the Mg2+, but I think the relative atomic mass for the Mg2+ would be 24.4, I guess, because for the equivalent per weight is 12.2.
But it's pembulatan lah. Okay.
Yeah. It should, because
okay.
Yeah. Yes.
Thank you, Pak.
Yeah, no problem, Pak.
But is that answering your question, Kevin? Yeah, because this one, the compound in the water, it will be in the compound form, right? So it will be in NaCl or MgCl2 or maybe MgSO4, like that. But when it dissolves in the solid, it dissolves in the water, it will be in the ionic form. So like dissociation form. And depending on the AR, the ion weight, and the valencies, the ability of like sodium to get the chloride ion and the ability of the magnesium to get the chloride ion is different.
Yes, sir. I kind of understand already.
Huh?
Yeah, I understand, sir. It's like
that's why you need to normalize it. When you do the calculation, basically equivalent weight is to normalize the weight of one ion, right? One ion. So the weight is this one. For one ion, depending on the valencies.
Yes, sir. I understand, sir.
Okay.
Thank you, sir.
Okay, because if you calculate just the ppm, the number will be different. But just to check whether the calculation of this ppm or the analysis of the concentration is already correct, you convert it into EPM, then you compare the total one. It should be the same. If it's not the same, then the value here is still not correct. It means you do not get all the total dissolved solids in the water. Okay. The concentration is also can be presented as ppm equivalent calcium carbonate. Yeah, so the conversion will be ppm, the concentration, times this one, calcium carbonate equivalent with, this is the molecular weight, mr ya Pak Indra, divided by the ion equivalent weight. So 1 ppm of Ca ion will be equals 5. 50 is the mr of this one. This is the ion equivalent weight. You get the ion equivalent weight from this one. Okay, so if you convert it further, the data, you convert it into the ppm CO calcium carbonate, you can get the numbers, different numbers. But if you sum up of the cations and compare it to the sum of the anion, it should also it should be similar also. Ya, itu cara menyatakan aja. Dan menyatakannya itu selalu nanti dalam ekivalen. Bisa dalam ekivalen per million, EPM, or ppm CaCO3. Yeah, normally hardness is represented using this unit. Okay, any question? Okay, other parameters that normally used is conductivity. Anyone know conductivity? I think the name itself is already explaining the parameters. What is conductivity? If you have high conductivity of solution, what does it mean?
The ability to transport energy, sir, through the solution.
What kind of energy?
It can be heat or electricity, sir.
Yeah, it's related to electricity. Yeah, the basically if you have pure water, yeah, because there is no ions inside, the water cannot how to say, transmit electron. Is it the correct term, Pak Hendra?
Or electron transfer, ya, Pak?
Yeah, it's the higher the conductivity, the electron transfer will be higher. So how to make the water with how to increase the conductivity of the water? Then you add salts into the water. Yeah, why this conductivity is done? I mean, why you need to test the conductivity of the water? So basically, the conductivity is related to the concentration of salts inside the water. Anyone can guess why you need to measure the conductivity?
Sir, so we can know like how much impurities is contained in the water?
Yeah, why you do the conductivity test? Why you do not do the this one? Okay, maybe Helena, if you have water with NaCl solution, right? NaCl compound, how can you get the concentration of salts in the water? If you have brine solution, it contains NaCl, yeah, salt solution. How you get the concentration of the NaCl in terms of milligram per liter? Any idea? Kalau kamu punya
Titration.
titration, is it correct, Pak Hendra? Can you do titration to get the concentration of NaCl? For example, if the solution is very salty, the concentration of NaCl is very high. Then you want to calculate the concentration. How you produce salt in real life? Cara dapat garam itu biasanya gimana? Dari air
Dikeringin,
laut.
sir.
Sorry?
Dikeringin, sir.
Yeah, to evaporate, right? Yeah. So you evaporate this solution. So the water will evaporate and leaves the salt. We call it the gravimetric. So basically gravimetry is not just evaporation. You heat it up the solution until certain temperature, and then you get the suspended solid, and then you filtrate it, and then you dry it, and then you measure the weight, right? Ya, kebayang ya. Jadi dipanasin, nanti airnya nguap, padatannya tertinggal. Nanti kalau semua sudah jadi padatan, tinggal dipisahkan, terus ditimbang gitu ya setelah kering. That's the principle of the gravimetry in briefs. Okay, that only can be done if the concentration of salt is quite high, right? Okay, for example, in a high pressure boiler, the maximum salt concentration is only 2 ppm. 2 ppm. It means 2 milligram per liter. Jadi dalam 1 liter, garamnya itu maksimal 2 miligram. 2 miligram itu sebanyak apa atau sesedikit apa? 1 teaspoon. How much is 1 teaspoon? 5 gram. Sendok teh ya, bukan sendok makan. The teaspoon one, the small one, is 5 gram. 2 milligram is like divided by 1,000 in 1 liter of water. So that's a very, very small amount of salt. Ya, jadi dikit banget. Cuman 1/1000 kurang dari 1 sendok teh dilarutkan dalam 1 liter. If you do the gravimetry, can you imagine how tedious it will be? Yeah, you have to evaporate it, and then you just got a small amount, and maybe the calculation is not accurate. But for the boiler feed water, this is the maximum you can go. Then the how to identify or how to calculate the concentration, we use the conductivity method. The ability of the salt solution to transfer the electron, to transfer the electricity. Yeah, so you can use this test to replace the gravimetry method. Okay, the reverse, the opposite of the conductivity, we call it resistivity. Yeah, resistivity is the inversely proportional, and as the rule of thumb, if you have water at around 5 to 9, the pH is around 5 to 9, the concentration of salt will be around 0.65 times the conductivity. Okay, the conductivity unit is micromos per centimeters or microsiemens per centimeters. So this is the relative value. If you, I think you can see, right? This is ultra pure water, deionized water, tap water, seawater, and sodium hydroxide solution. Okay, yeah, resistivity is 1 over conductivity, and the unit will be mega ohms centimeters, 1 over conductivity. Okay, the other, any question until this part first? Ada yang mau tanya nggak? Lanjut ya. Okay, we go. And then the other properties of the water will be pH. pH basically represent the concentration of hydrogen ion in the water. Yeah, so you learn hardness, conductivity, resistivity, and then alkalinity is basically, and pH is basically basic chemistry. So please don't forget that's why you need to learn about basic chemistry when you do the TPB, because it will be used in this lecture. So this is the pH, and for processed water, or in the boiler water, on the cooling tower, cooling water, is normally the pH should be around neutral or slightly alkali because of the corrosion potency that we will encounter if you have acidic water. And then also the carbonate, previously I mentioned carbonate. Carbonate can be in the form of carbonate itself and can be in the form of as the CO2 can be in the form of carbonate, bicarbonate, and can be in the form of carbonate. And it will be influenced by pH because it's all in the equilibrium. And beside pH, it also will be influenced by the concentration itself. So please remember again about the equilibrium properties. If you have a lower pH, what will be happen? Lower pH means what?
It will shift to the H2CO3, sir.
Yeah, why? Why? Can you explain? Not based on this one, but based on this one. Because at lower pH, it means you have high hydrogen concentration, right? So if you have higher hydrogen concentration, the equilibrium will be shifting to the left. Like there will be more bicarbonate and still higher hydrogen concentration. There will be more this one. How we call it in English, Pak Hendra?
Pak, carbonic acid, Pak.
Carbonic acid, okay. So
or maybe we have to also know regarding the principles, but for the reversible reactions, we call it Le Chatelier principle. Pak.
Yeah, Le Chatelier principle.
Le Chatelier principles. Yeah.
So depending on how much the compound, it will be shifted to the other side of the reaction, right?
Yes.
So if the Pendra, sorry.
Yes, correct, Pak. Yeah.
Okay. So if you have a lot of H2CO3, if the pH is continued to be lower, then you will have this one. It means it will be in the gaseous form. This is the dissolved form, and this one is the gaseous form. So if carbon dioxide is dissolved in the water, it will be in the carbonic acid, and the carbonic acid will be dissociated into the bicarbonate, and bicarbonate will be dissociated into carbonate. And the pH will influence how much of each compound. What will be dominant in the water? You can see from this one, right? So if you go to this one is carbonic acid, and then this one is HCO3, and then this one is CO3 to minus. Okay, as the summary, some properties of the water, the impurity of the water, will have unwanted effect if you want to use the water in the process, like hardness. Basically, it will create a scaling on boiler and also heat exchanger. So if you have scaling, it means if it's in the heat exchanger, the exchange of the heat, the heat exchange will be reduced. The thermal efficiency will be reduced. Ya, jadi perpindahan panasnya kan tidak akan terhambat. How about the sodium? Sodium can cause denting. Denting itu bukan denting ya, ini tuh penyok ya. Do you know penyok? Denting, you know, right? Can cause denting, like the pipe will be like Ya, itulah how to call it in Indonesia. Then can pitting. So pitting is very small hole in the pipe, and also the formation of natrium hydroxide. It will be if you have pitting or denting or anyways, it will cause leaking in the pipe, corrosion in the boiler or the heat exchanger. How about the chloride sulfate? It will create the corrosion, and also will have you will have leaking pipe in the boiler, for example. And silica, we have mentioned about silica. It can create what we call plating out or glazing. Yeah, plating out is like layer of very hard substance like glass in the boiler, or later can be carried over in the turbine. So it can carry it over to the turbine. Yeah. And then because maybe the steam that produced by the boiler is used to move the turbine for the steam turbine, so it can reduce the thermal efficiency. Okay, I think we have shows these numbers. I add one more. This is the SME guidelines for the water quality in waste tube boiler. So you can see from in terms of some dissolved minerals like iron, copper, hardness, silica, and alkalinity. Yeah, the higher the pressure, it will require, what is the difference between boiler water and the boiler feed water? Boiler water is the water inside the boiler. Yeah, so this is the requirement. And this one is boiler feed water, the water that you need to feed into the boiler. So the specification should be much lower than boiler water. Okay, and maybe a bit about this one. This one is actually this effect or the impact will not occur directly. Yeah, like if you use hardness water or use high content of silica in the water, then you use it once and then just the boiler will broke or something. No, but it will happen eventually. Like in the long term, it will happen. But once it happen, the remediation, the repair will be very hard. Yeah, the effect will be very, very severe, and you need a lot of money to repair the damage. Yeah, that's why it's very, very it's very, very costly for the repair. So that's why the industry need to make sure that the water that they use is meeting the requirement. And that's why there are some companies, I think I have told you, some companies are focusing just in treating the water and then sell the water to the industry. Because the infestation and the operational cost to treat the water is quite high also. But the repair will be higher. If you have damage in the boiler, for example, your tube boiler is bursting or the heat exchanger is scaling, then the cost to open the heat exchanger and then change the tube or cleaning the tube in the long term, it's much higher than the cost of water treatment. Okay, any question? Okay, then we go to the next part, which is the water treatment process. Okay, water treatment process is basically the process to treat water in order to meet the requirement. But we can classify the water treatment process into two big categories. First is what we call external treatment. Yeah, it's not the one that we call it external. Internal is not like we do external treatment outside the plant, no, or this one is inside the plant, although it can be happens like that. But external treatment is basically the general treatment to treat the water for general requirement. ya. Jadi ini bukan terus dilakukan di luar, ini dilakukan di dalam pabrik, ini dilakukan di luar pabrik ya. Tapi memang yang ini itu external means it's outside the main process. While the internal, it's directly related to the process. You can see that for the external treatment, maybe later you can, when you heard about water treatment, in general, it the external treatment because it's general water treatment, and sometimes it's not until demineralized, maybe it's just until the potable water. But for the internal treatment, we call it water conditioning. So if you heard the term water conditioning, it's actually the internal treatment. Ya, jadi istilahnya biasanya ya sekarang sih sering disebut internal dan eksternal ya. Tapi kalau baca-baca buku mendengar istilah water conditioning, it will be correlated to the internal treatment. Okay, like if you need to supply the boiler with the feed water, then you have to do the external treatment first. Yeah, you do the external treatment first. First for the groundwater, you neutralize using base solution. It goes to the aerator, and then you go to the filtered, and then you go to the filtered water. And basically, after you filter the water, basically you can use it directly as the potable water by adding the chlorine. And the filtered water, if you want to use the water for the boiler, then you have to make it into the demineralized water. So all the minerals should be gone. Then you do the cation anion exchanger. Okay, after this one, then you go to the internal treatment. Internal treatment normally is done by adding some chemicals. So at this point, you add hydrazine. Hydrazine is to reduce the oxygen. Hence the name is the aerator. And then it goes to the boiler, created the steam, used in the plant, and become the condensate. Condensate is the water comes from the steam, because the temperature is already reduced, the pressure is already reduced, that it become condensate. You do not throw away the condensate because the cost of this one is quite high already. So after the steam become condensate, normally it will goes to the condensate polisher. So it's like to clean up the some residue that may be carried over by the condensate, and then goes again to the aerator and used to the boiler. So it's like the recycle for the boiler. Yeah, this is one example of internal treatment. Okay, now we see video first is about the water treatment process in general. So I can also have a break for some minutes. So please watch the general water treatment process, and then we will discuss it further.
water is one of the largest drivers of creating a modern society. But what allows everyone access to seemingly endless supplies of potable water? It depends on where you live, but chances are behind your tap, there's a municipal water treatment plant. There are two main types of water treatment plants: drinking water or wastewater plants. We'll be focusing in on drinking water plants here, but if you'd like to learn about how wastewater is treated, you can watch the video linked in the upper right here. The question still remains, how exactly does one treatment plant take dirty river water or well water and turn it into water that is safe to drink? It involves a lot of processing, using chemicals, filters, and removing all of the toxins and hazards from a given source. The entire process starts with something called coagulation and flocculation. All drinking water has to come from somewhere, usually being freshwater lakes, rivers, wells, or streams. In these water sources, there's going to be some amount of sediment as well as organic materials in the water. These particles of sand, bacteria, dirt, wood, etc., they all have to be removed before the water can be sent out to city residents. To do this, chemicals called coagulants are added to the water. These chemicals, such as aluminum sulfate or ferric chloride, work to help the particles in the water congeal together. Essentially, these chemicals have the opposite charges of suspended solids, like clays or silts. When combined, the charges of the particles are neutralized, allowing for them to stick together. Coagulants are often added to the water right at the inlet of a drinking water plant, where the water then goes into mixing basins called flocculation basins. In these basins, the solution of water and coagulant will slowly be mixed together to form what are called floc particles. After mixing for a set amount of time determined by water quality in the flocculation basins, the water is moved to sedimentation basins. It's in these holding tanks where the water sits for the floc particles to begin settling out at a faster and faster rate, which is the intended goal of this process. By simply adding and mixing these chemicals into the water and letting that water sit, a large portion of the sediment will settle out to the bottom as sludge, which can be taken away to a landfill or holding facility. The floc particles are ultimately removed from the bottom of basins, and the clean water, being the cleanest at the top due to the settling particles, flows over weirs to the next stage in the process. In some plants, engineers actually use dissolved air flotation tanks in place of sedimentation basins. In these cases, air is pumped into the bottom of the tanks, creating a cascade of tiny bubbles. As these bubbles float to the surface, they take floc particles with them, forming a film of floc on the surface of the tanks. Then, a sweeper arm pushes the floc into a collection basin where it's taken to a handling facility. In dissolved air flotation tanks, the clean water is taken from the bottom, where the least amount of floc is. When it comes to designing wastewater treatment plants, engineers will vary techniques based on the water source and how they want their final water to taste, feel, or otherwise be treated. The only regulation is the quality of water being pumped to the city, and in most cases, it doesn't matter how plants get the water to that point, which allows civil engineers a lot of creative freedom in the process. After the majority of solids are removed from the water during coagulation and flocculation, followed by sedimentation, the water flows over weirs to the next step, filtration. The water at this point will start looking clear, but there will still be bacteria and very small suspended solids in the mix. The filtration process will seek to remove the remainder of the suspended solids and bacteria to further bring the water up to snuff. Nearly every potable water treatment plant will use a sand filter for this process. Even in plants where engineers may not think it's needed, often sand filters will be added simply for extra measures to ensure clean water at the end. Sand filters are exactly what they sound like, a basin of fine to coarse sand that filters water. It would theoretically be possible to treat drinking water with only sand filters, but that would result in frequently clogged sand filters, resulting in lower efficiency and more cleaning time. These sand filters can be set up in essentially two different ways. Either the water flows from the bottom and exits the top, or the water flows from the top and exits the bottom. Each layout presents its own set of unique problems, but the most common technique is actually for the water to flow from the bottom to the top. Sand filters aren't highly technical. Water just passes through them and to flow through. However, while not highly technical, sand filters are highly efficient. Water flowing out of sand filters will need to have a clarity of around less than 0.3 nephelometric turbidity units, or NTU. Try saying that 3 times fast. Or whatever local code is used for water clarity. This measurement is essentially just a way to determine the number of particles still remaining in the water, or turbidity. Many treatment plants will also pass water through activated carbon basins, which you can essentially think of as giant Brita filter tanks. Activated carbon particles have hundreds of tiny pores on them that help remove the tiniest of sediment and bacteria. This process isn't wholly necessary, but it helps improve taste and odor, often a desired trait for city residents. At this point, the water should be mostly crystal clear, but there still remains some residual bacteria. That leads us to the next step, disinfection. There are 3 main ways of disinfection in the water treatment process, which can be used individually or in combination with one another, depending upon design. First, chlorine or chloramine treatment, there's ozone treatment, and finally, ultraviolet radiation treatment. In the US, the main method of disinfection is by adding chloramines, or chlorine-based compounds. These compounds, such as chlorine dioxide or monochloramine, work to kill microorganisms. One downside to this process, though, is that these chemicals can react with other organic material in the water to create disinfection byproducts. These disinfection byproducts are harmful to human health and have to be prevented or mitigated. This extraneous reaction with other organic material is also why chlorine disinfection must come at the end of the treatment process. If added at the beginning, an abundance of disinfection byproducts would be created, causing a plethora of issues for the engineers and plant operators. Even with all of this, chlorine is used mainly because of how it kills pathogens. It not only kills any pathogens in the water at the plant, but residual chlorine levels also remain in the tap water, killing any contaminants that might get introduced after leaving the plant. Most cities or states will have maximum or minimum chlorine levels in the treated water in order to keep both the water treated and city residents safe. The other most common method of treatment is ultraviolet radiation. In this process, UV light is shined through the water, which scrambles any bacteria's DNA. This doesn't kill the bacteria, but it makes it impossible for them to reproduce, thus making them harmless. The main downside to this disinfection process is that it isn't residual like the chlorine, meaning that any bacteria introduced to the water after this process can't be treated. Finally, we're left with ozone treatment. This process involves adding ozone, O3, to the water. Called ozonation, the ozone kills the bacteria in the water as well as improving the taste and odor. In most cases, this treatment process also requires that a chemical be used to remove any ozone at the end, such as sodium bisulfate, as not to cause any harmful effects to the city's population or anyone who might drink the water. After the water is treated, in any one of these 3 disinfection processes, it's ready to be pumped into a city's pipe network for delivery to your tap. The water flowing out of a plant is tested for various levels of chemicals, particles, and other qualities all outlined in a plant's permit. This permit, set by the governing agency, regulates water quality and holds the treatment plant accountable in the treatment process. At this point, all the water is fit for human consumption per the permit, and the treatment plant is tasked with keeping it flowing through the pipes in your city. Constant pressures of 40 psi must be kept at the outlets of the water in the system so that in areas of high elevation in the pipe network, the water retains residual pressure. 1 foot in water elevation is directly correlated to an increase or decrease of 0.433 psi. So as water is pumped throughout the city, its pressure at any given point of differing elevation fluctuates. Positive pressure always has to be achieved as to not let any external water in the ground flow through pipe cracks or joints. This would contaminate the entire system and is one reason why you might experience a boil water notice. Essentially, that means engineers have reason to believe that somewhere in that city's pipe network dropped below the required PSI and water or contaminants might have infiltrated the system. Massive pumps at the treatment plant supply pressure to the system through constant operation. Some of this pressure can be stored as elevation in water towers, which can give pumps a backup in emergencies or fire flows. In a lot of cases, water towers allow the pumps at the treatment plant to run at a constant rate, which increases efficiency and removes downtime problems. This combination of pumps and water towers allows your tap to remain flowing and otherwise allows you to live in the comfort of your own home. Civil engineers and treatment plant operators work around the clock to provide clean water water through water treatment plants. At this point, we've taken a look at the most common potable water treatment techniques, but there are tens to hundreds of other deviations we haven't discussed. This draws back to one of the coolest things about water treatment plant design. You're able to use any number of creative solutions to clean the water, and as long as it comes out clean, you've done your job well. Don't forget about the thankless job of being a water treatment plant operator, though. These men and women work around the clock to keep treatment plants running 24/7, so you can always
Okay, I think the last part of the video is not really important. It just shows that you can apply to this kind of company that focusing on treating the water. So the video is about more about the potable treatment, water treatment. It means the water that you can use for drinking purpose, but basically for the steps of the treatment is similar to the water treatment, the external water treatment that normally used in industry. Although maybe like chlorination or maybe the UV disinfection is not necessary, but you already hopefully you get the steps already. So basically, for the external treatment, yeah, is classified into three groups. First is pre-treatment, right? Pre-treatment is normally used for cooling water, yeah, air pendingin, or for early process. It consists like sedimentation, aeration, clarification. So the main purpose is to separate the suspended solid or clearing the smell, yeah, reducing the smell, reducing some compounds that easy to be reducing the hardness, something like that, and then easy to be employed. So it can be done in the first step, although there are quite numbers of operation that you can choose, depends on the purpose. And then the second one will be the filtration. Filtration is after you not, yeah, after you separate you concentrated the suspended solids, then you remove the suspended matter. So you can use either by a filter or by membrane, depends on the purpose as well. And the third one will be the hardest one, is to reduce or remove the dissolved solid, because dissolved solid is not something that visually visible, right? So all are in the dissolved form. So depending on the characteristic of the dissolved solid, the compounds, the ions, then you can employ several steps. You have option of step how to reduce or remove the dissolved solid. For example, by using the ion exchange. Yeah, this is basically the one that we have discussed, the same process that we have discussed before. Yeah, if you have, oh, this is still in Indonesian. Okay, if you have air baku, ya, jadi ini adalah bahan baku. This is the raw material, the water. I mean the water for the utilities, and then it should be goes into the clarifier. This is the step A, and then go to the step B. So you can have the group A, and then you go to the group B, and then you have a clear well water. So basically, this clear well water can be directly used for the hydrant system, the fire extinguishing, or for the industrial water. Or it can be also used for the cooling tower purpose as the cooling water. But of course, you need the additional treatment. So this is the internal treatment. You add chemicals to treat the cooling water. the clear well before goes to boiler, for example, like it goes to the exchanger and then go, to remove the mineral, then it goes to the ion exchanger and then goes to the aerator and then goes to the boiler. Yeah, this is the types of combination of external and internal water. Yeah, this one is the other types. Yeah. Okay, then we go to the unit operation one by one. The first one is to concentrate, to accumulate the suspended one before it can be separated. So the process, we can call it sedimentation or clarification. Yeah, this is to precipitate because suspended means not dissolved, but it's not mengendap apa bahasa Inggris? Yeah, it's not at the. Sorry.
Agglomerate or precipitate.
Yeah, it's not in the precipitated form. It means the suspension will be melayang-layang in the water. Yeah, it will be suspended in the water. So we need to concentrate to precipitate, and either by making the size larger or making the suspended solid become heavier. Yeah. Actually, making it larger, it becomes heavier, and then it will be agglomerate, and then it will be precipitate. Yeah, this is the first step. Yeah, the sedimentation. I think you can check your fluid mechanic slide last year, and then you can see that the sedimentation will be depending on the density, the shape, and the particle size. Yeah, that's why the operation involving increasing the size. Because by increasing the size, then you increase the density. Then it will be precipitated. And it will be also depending on the viscosity and also depending on the flow rate and the flow type of the fluid. Yeah. So this is the process. Yeah, the process is usually done before clarification, before it can be clarified, because before it can be separated. So but the name sometimes it's clarifier. Yeah, you can use either the sedimentation tank or you can use in clarifier tank. Okay, so it has this one. The arrangement is like this one. The water will flows from this side, and then due to the arrangement of the clarifier, it's a bit slanted. Yeah. So while it's flowing, you can add some chemicals. So while it's flowing, the suspended solid will agglomerate and then will fall down and then will accumulate at the bottom of the tank. Yeah, this is the simple rectangular tank, or you can add what we call lamella. Lamella is like layers of plates here to help the clarification, to help the agglomeration of the particle. Now, this is also the main, general types of sedimentation tank. Yeah, so it's also slanted, and the water is flowing from the bottom of the tank, and then the solid will be goes to the bottom again, and then it will be separated. Yeah, this is the sedimentation and clarification. And then the second one is aeration. So this one normally done when the suspended solid content is quite a lot. It means you have a lot of solid particles. So by adjusting the flow, yeah, because you will have water flowing, right? But the flow rate will be very, very slow. So while the water are traveling from the inlet point to the outlet point, the suspended solid will be flowing down. Yeah, and then if necessary, you can employ the aeration. Aeration in water treatment basically used if you have unwanted metals like iron and manganese. Basically, if you when you do the aeration in mechanical way, it helps mixing the water with air, right? But basically, but if eventually you provide more oxygen from the air, and then the oxygen can oxidize the iron or manganese. Then it will be precipitate. Also, by do the aeration, it also helps removing the gases, especially corrosive gases like hydrogen sulfide. So it will be purged out by the air. If the water contains some smell, flavor, or color due to the microorganism that growth in the water, maybe they produce a certain gas or smell, then by aeration, by oxidation, then it will reduce the smell, flavor, and color. Yeah, the oxidation of iron and manganese will result in the insoluble iron, and then the precipitate will can be removed by the filter. Okay, this process will be optimized by adjusting the temperature, the contact time, the surface area, and also the ratio between air and water. So the unit will be like this. Yeah, the water will come from the top part of the aerator, and then the gas will be supplied from the bottom, from the blower. Yeah, so there will be counter current contact, ya, kontaknya counter current, airnya dari atas, gasnya dari bawah. That's why the clean water will be accumulated at the bottom part. So the unit should look like this. This is the blower, and the water are delivered from the top part, and then the process, the aerated water will comes from the bottom part. Okay. Okay, the next one will be coagulation, flocculation, and clarification. So basically, this one is the process to add more chemicals. If previously in the sedimentation, the separation of the solid from the water is mainly it's because of the gravitational force. But in this process, the coagulation, flocculation, and clarification, you add more chemicals and provide mixing. In the sedimentation, you do not provide mixing, it's just water flowing. But in this coagulation, flocculation, and clarification, you will have mixing. So basically, this one that will happen. Coagulation is the process of neutralization of charged particles. So why it's always suspended? Because it has charge on the surface. And because each particle has charge, they will continue to be suspended in the water. So we can add some coagulant, we call it coagulant, and then we do the fast mixing. So the purpose of the coagulation is to decrease or to remove the charge on the surface particles, on the particle surface. Then it will be continued to slow mixing. What will happen in the slow mixing, in the flocculation, the small particle will combine and they will form bigger particle. We call it floc. That's why the process called flocculation. Then the mixing is much slower than the first one. So this one is fast mixing in the short duration. This one is slow mixing. The duration is quite longer. And then the next step will be clarification. This is to used to remove the suspended solid. and then the water can be treated further. Okay, this is the reaction. That's the chemicals is aluminum based or natrium based or ferric based. Or we can use the coagulant. Coagulant is to help the reducing the surface charge. This is the brand, the type of the coagulant. So this is the reaction that may happen. So not all happen depending on the coagulant and the flocculant. Okay, this one is the diagram. Yeah. So first is the flocculation. Yeah, the fast mixing, and then it continues with slow mixing, and then continues with the settling. This one is also the same: fast mixing, slow mixing, and then settling. In the sludge blanket, so the mixing is happen in this area. Where is the inlet? The inlet should be from this one.
On the left-hand side, Pak.
Oh, this one is left. Okay. This one, okay. Yeah, this is the fast mixing happen here, and this one is slow mixing. And then after going through this part, the flock, the bigger flock, will be settled at the bottom. So the clean water will be here, and the sludge will be accumulated here. Okay, before we go to the filtration, I think we'll continue tomorrow. I think I will try to show you this process. I think this short video. Just a minute.
Flocculation and coagulation are fundamental for wastewater treatment and were already used by the ancient Egyptians in 1300 BC. This sample of muddy-looking water from a paper mill has a very high turbidity due to the presence of many suspended particles. Adding flocculants will cause that the small particles clump together to bigger flocks that settle down. So let's have a closer look how flocculation and coagulation work in detail. Turbidity of muddy-looking water is caused by two types of particles, organic and inorganic. Organic particles are, for example, algae and bacteria, whereas inorganic particles are, for example, clay and silt. Both particle types have in common that they are able to float because they are too small to settle by gravity. Suspended particles that are too light to settle down are called colloids. Almost all colloids have negatively charged surfaces. The negatively charged surface will attract positively charged ions in the water, so the colloids form a first layer. The effect is very similar to magnets. Like poles repel, but opposite poles attract each other. Over time, colloids form a second, diffused layer with positively and negatively charged ions called a double layer. The double layer creates a responsive force which prevents two colloids from stacking to each other. The colloids stay suspended in water and move around to avoid collision with other colloids. To overcome this behavior and to clump colloids together for particle settling, flocculants are used. Typical used flocculants for particle settling are alum and ferrics. Alum and ferrics are ideal as flocculants because they form a high number of ions when they get in contact with water. These ions will bind together with the colloids and neutralize responsive forces. Mixing the water allows the colloids to stick together. to form bigger flocks and settle down to the tank bottom. Within wastewater treatment plants, the flocculation process is normally separated from sedimentation. Under gentle agitation, flocculants are added in the mixing tank before water is entering the sedimentation tank. Here particles are settling down until they build up a sludge blanket, which is then removed. Thanks for watching, and if you like our 3-minute tutorials, please subscribe.
Okay, any question? Ada pertanyaan dari mahasiswa? Okay, that's the video shows you the basic principle of the coagulation and flocculation. Hopefully it helps you to understand. And then if you have no question, then we'll continue tomorrow about the further treatment for the water treatment. Okay, thank you and good afternoon. See you next week.
Thank you very much,
Thank you,
sir.
Thank you, sir.
Thank you,